Hello everyone, my name is Zhuo Xu and I'm a PhD student from the Norwegian University of Science and Technology, Department of Mechanical and Industrial Engineering. Today I will present our research work, Quasi-static behavior of 3D printed lattice structures of various scales. It is my pleasure to present the research work here, and I would like to take this moment to thank Elena, Fabrice, Filippo, and my supervisor, Javad Razavi. I couldn't accomplish this research without the support from them. Okay, so this is the outline for this presentation. First, I will talk about the background, motivation, and literature reviews. And also next, I will be talking about fused deposition modeling, which is FDM fabrication process of the lattice structures. And next, I will be talking about some steps of the experimental procedures, and in the end, I will get to some of the results and conclusions. So the aim for this research is to investigate the scale and the wall thickness effect on the mechanical properties of various uniform lattice structures. First, let's talk about a little bit background of additive manufacturing. So for additive manufacturing, technology has been playing a significant role in industrial applications because its potential capacities to fabricate complex geometry. As you can see from this figure, no matter it's from the geometry design of the view or the material design, and also the tooling process development, 3D additive manufacturing has been playing a very important role in our life, also in the industry as well. And the application is covering from the nanoscale range to the large scale range. For example, some of the application including the fabrication, which is a very small scale range, and to some of the automobile and aerospace and defensive, which is the large scale model. There are some motivations for this research project. First, lattice structures are treated as outstanding candidates for a lot of applications. For example, for biomedical implants, lightweight energy absorption, and heat dissipation from relatively small to large scale, as I was mentioning before. And second, as the results from our literature review, there is a high dependency of the scale, geometry, and the wall thickness effect on the mechanical properties of the conventional design parts produced via additive manufacturing. So these images are some of the applications of lattice structures. For example, the first image shows the artificial hip joint, and the second shows the firmware fabricated with selective laser melting technology with the material of titanium alloy and aluminum alloy. Okay, so this is uniform gyroid lattice structures. So these are the lattice structures that we were using for this research. So what are the uniform lattice structures? What's the definition? So it is porous structures that combine three-dimensional unit cells periodically with a fixed volume fraction ratio, which means it has a constant density or the porosity of the lattice. And this is a TPMS lattice. TPMS is a short abbreviation for triply periodic minimum surface lattice. And in general, the lattice has three types. The first one is called struct-based, the second one is solid TPM-based lattice, and third one is the sheet TPM-based lattice. And as you can see here, these are the unit cell lattice for the sheet-based dry road. This is 1 by 1 by 1. And these are also the sheet-based dry road, but as the larger dimension as 64 unit cells. So the dimension is 4 by 4 by 4. And for the mathematical equation, it has the level set method. We call it LSM for short, and this is a methodology framework primarily used for the numerical analysis of the surface and the shapes. You can see these X stands for the function of alpha, beta, and gamma here, and also C is an ISO value. Alpha, beta, gamma are the constant corresponding to the unit cell in the X, Y, and Z directions. Okay, so these are the fabrication process and some lattice parameters we have determined prior to the experiment. So for the 3D printer, we used Prusa i3 MK3 for this research. It is a very good printer for printing PLA and has a very good resolution, and it's also very stable. And we have the filament brand 3D net 1.75 millimeter for diameter. And the slicing software we use is the Ultimaker Cura 4.8.0. And the printing sequence we have is one at a time, so which means we're not doing the parallel printing. Instead, we have the one by one printing, which means we print lattice. We will finish one lattice and then move on to the next one. And for the lattice dimensions, because we are studying the scale effect, so we want to get the smallest lattice as small as possible, but in the meantime, we also want to maintain the good quality. And for the largest one, because of the limitation of the print bed and also our testing machines, so we want to get the largest as possible. And we have 3 categories for our research for that, and each case was tested at least 3 times to make sure, to make sure this is not something random, and we take the average and we will calculate the standard deviation. So as you can see, we have 3 categories here. We are studying the scale effect, and we keep the constant porosity here. So in this case, the porosity is all constant. The others are the changing variables. And we have the wall thickness effect. In this case, we keep the constant cubic size and the unit cell size. And also we have the geometry effect, which in this case, we have the constant wall thickness, and the rest will be the variable. And this is the lattice dimensions and process parameters for the printing. And as you can see here, we have in total 10 types of lattices to be fabricated. And the G here represents dry road, and 4 is the unit cell size. And for example, in this case, 0.645 is the wall thickness. So these are the naming rules for the lattice. And this is the process parameters for the printer. And we have some trials and errors here. And finally, we have determined to use this process parameter because it produced the best quality lattice, at least visually. And for the layer height, we chose 0.15 in this case. And also for the retraction distance and the filament, we have 0.5 millimeter and the 35 millimeter per second. So in this case, we have tested to make sure that there was no straining issue between the lines of the printing. So this is the compression behavior of two of the lattice sets. In this case, one would be the thickness of 0.645 and the other is the thickness of 1.29. As we can see, these images are selected based on the different strain percentage of the lattice. 0 would be the initial status before starting experiment, and the lattice was compressed eventually to 50% of the string, and you can see the behavior of each layer, how was it behaved under the compression behavior. And this is the digital image correlation analysis. We call it DIC analysis. And this is a video for that. And for the analysis, we have the subset of 29, which subset is the tracking area for the dots for the DIC analysis. So the larger the subset, the larger the tracking area would be, but also creates a larger uncertainty. And in this case, we have step three, in which it means for every 3 data points of the DIC, we choose 1 point to analysis. And the label V here is the distance along the y-axis. As you can see, I can play on this video here, and as you can see, the filling pattern is it's filling layer by layer, and it's starting from the bottom. As you can see, the displacement from the bottom is higher than the top, and it's starting from the bottom and propagates to the top. And for this animation frequency, it's 5 frames per second. As you can see, while the bottom is fading, the DIC kind of lost the track for that. As we can see the results here, we have stress strain plots, and we have an cumulative energy absorption per unit volume versus strain plot. And from those two plots, we can get some conclusions. First, lattice with larger scales experience higher ultimate compressive strain under constant porosity. This can be concluded from the first plot here. As you can see, the peak stress here, and all the curves reaches the ultimate compressive strain and the densification point, which is the lowest point of that, at nearly the same strain regardless of the wall thickness and the scale under constant porosity. And also for the cumulative energy absorption per unit volume, large scale and the larger wall thickness will slightly increase, as you can see from the plot, the cumulative energy absorption per unit volume under constant porosity. And these are other two sets, and also we have the stress stream plot and the energy stream plot. We can get a conclusion of first, relatively higher porosity and smaller wall thickness will have multiple peaks during the compression process, as you can see from the curve here and the curve here. These are the lattice with relatively high porosity, so which indicates might be possible buckling of the structs under layer by layer filling mode. And also the lower porosity lattice tend to reach the decimal point at relatively smaller string, and also all the lattices show linear trend for the cumulative energy absorption within 0 to 50% of the string here. Okay, that's the end of my presentation. Thank you for watching. If you have any questions, please contact me.